It's rather difficult to create the perfect Cartesian surfaces that create perfect images. And so we're usually working with spherical surfaces. So our first foray into image formation will be to look at a mirrored sphere. And so this blue surface right here represents the spherical mirror, which has radius capital R and its center right here. And then I'm just going to choose a single object point. That object point will be right over here, and so we need to figure out where exactly the image of that thing is going to form. So to do that, I'm going to take just a single ray coming from the object. Remember that there's multiple rays coming out. I'm just going to pick one to track and try and figure out where the image is. So that ray hits right there. Now the thing to keep in mind with a sphere is that the normal of the sphere is always going to lie along the radius vector. And with a mirror, the angle of incidence is equal to the angle of reflection. So these two angles right here are the same. Now to locate the image, what I'm going to do is trace where the reflected ray looks like it came from. So just by tracing this thing back, and I know that my image is going to lie on the optical axis just like the object does, and so this then is going to be the location of my image right here. And so then I need to figure out a way to relate the location of the object relative to the sphere to the location of the image. So I'm going to call the distance between the object and the surface of the sphere S sub O, the object distance. That's to this point right here. And then the distance between the surface of the mirror and the image will be SI for image. So I need to find a way to relate those two quantities to one another. And so we're going to set up this geometry, and let's see, I'll call this angle in here phi, and this angle gamma. And now I need to start relating some of my angles to one another. So I noticed that this arc right here is 180 degrees. And with theta right here, that means that the difference between those two arcs, in other words, this right here, is equal to 180 minus theta. Now, that is the interior angle of this triangle, where the other two angles are phi and gamma. And so the sum of those three angles, in other words, the sum of this angle plus phi plus gamma, has to be equal to 180 degrees, which gives me theta is equal to phi plus gamma. The next thing to notice is I'm going to look at a slightly different triangle. I'm going to look at this triangle right here, and I'm going to call this angle down here alpha. It turns out that alpha and phi are actually closely related to S sub naught and S sub I, and so these are the two angles I'm actually going to be focusing on a little bit. Now, I do see that this angle here is 180 degrees. What I really want is this angle in here. So to get this angle in here, I'm going to take 180 minus 2 theta. So 180 minus 2 theta gives me this angle in here, 180 minus 2 theta. And so the interior angles of that smaller triangle are 180 minus 2 theta plus phi plus alpha is 180 degrees, or 2 theta is equal to phi plus alpha. All right, so now I have some equations that are relating theta and phi and all those things together, and that gives me a good starting point for my next step. So what I want to do is find a way to relate phi and alpha, since those are the angles that I'm associating with the object and the image. I need to relate those two. And so what I'm going to do is combine these two equations together, and that ends up giving me a relationship 2 gamma is alpha minus phi. Now, before we go any further, we have to make a couple of simplifications. This is why this is one of the crucial points to using spheres instead of the perfect Cartesian surfaces. So we're going to use what's called the small angle approximation. If you look at the Taylor series of sine, cosine, and tangent, you can write these out as infinite polynomials where each successive term has a higher and higher exponent in it. As long as our angle theta is much, much less than 1. What that means then is that the second term in each of these series is going to be much, much smaller than the first term. And so to first order, I can approximate sine, cosine, and tangent by just the first term in that infinite series, in that Taylor series. And so sine of theta is approximately theta, cosine theta is approximately 1, and tangent theta is approximately theta. This is a small angle approximation. This is used quite a bit in physics, and so understanding where this came from is crucial. You'll see it again and again and again. So using that small angle approximation, what we're going to do is use some of the lengths in our diagram to make some relationships here. In particular, we're going to need these relationships here, and I'll show you where those terms are coming from. If we define a height h in here to be this leg right here, forming a right angle with the optical axis, that h now can be used to find tangent phi, tangent alpha, and tangent gamma. So what I have is that tangent of phi is approximately, now notice this isn't working perfectly because I don't actually know this entire distance here, but I can approximate that distance by s naught. So the tangent of theta is approximately h over s naught. Similarly, with alpha, I can assume that the tangent of alpha is approximately h over si, and the tangent of gamma is approximately h over r, where I'm assuming that this distance right here is pretty close to r. Now this only works for small angles. The way the diagram is drawn, my angles are magnified. So if we were doing this in a real system, these angles would have to be very, very small, very close to 0 for this set of approximations to work. So what I'm going to do is use this along with the fact that the tangent of each of these angles is approximately equal to the angle. In other words, tangent alpha is approximately alpha. The tangent of phi is approximately phi, and the tangent of gamma is approximately gamma. And plug that into this equation right here. So what we end up getting is this relationship. Now I've got h in every single term, and so I can divide through by h and get those to cancel out. And I end up with, after just a little bit of algebra, this equation right here. Now, I need to define a sign convention for SO, SI, and R. In other words, when are these considered positive values? When are these considered negative values? And in doing that, I'll actually change this equation just a little bit. I'm going to end up switching the sign by my choice of conventions. So, R is considered positive for spheres. In other words, anything that has an outward curvature, not an inward curvature. We would say that the mirror needs to be convex, not concave, for R to be positive. The object distance is positive for the object outside the mirror. Now, how could the object be inside the mirror, you're wondering? Well, we will actually see that when you put multiple optical elements together, you can have images that are acting like they are inside the mirror. The one change we're making is we're assuming that the image distance is positive for images outside the mirror. Now, the image that we drew up above was inside the mirror, and so that would be a negative quantity. And so we're going to introduce that negative sign into our equation and rewrite our equation in this form right here, where all I've done is switch this from a negative to a positive. Then if we go ahead and define a focal length of the mirror by this equation, this is the result that I get. This is frequently called the thin lens equation, but it also works for mirrors. And there you have it.